you super excited? This is a hands-on session. You will be graded on effort, enthusiasm, and overall knowledge learned at the end of this course. I'm just totally kidding, so don't worry. Okay, so Tina has gone over some examples of what I was going to show, so different examples. But the idea here is, how do you take a Skyline file and optimize the settings so that you get the best parameters for your assay at the end of the day. So one thing is what we call refining a method, or refining transitions. And the idea here is, you might have a peptide candidate that looks great, it's got a lot of product ions, but you don't necessarily need to monitor all of them on a triple quad. You get all of them for free if you're doing parallel reaction monitoring, but if you have a triple, the number of transitions you're monitoring directly impacts your cycle time, and you might not want to monitor all 9 or 10. So the idea is, how do you pick the best ones? Also, when you're doing optimization, it's always best to do it on the instrument where you're actually going to be running the method routinely. Whether it's you have 2 instruments of the same model, you should be able to ping pong them back and forth reasonably well, as long as you are showing data that's pretty consistent. But I wouldn't recommend optimizing in PRM mode and then transferring it to a triple quad without doing triple quad optimization. And then optimizing your transitions will provide you with the best quantitative results. This is particularly true for the triple quad. So please, everybody, open up the Skyline program, and you will get to a blank, click on the blank document option, and you should get something that looks like this. Let me know when you're ready. Good, all right? All right, that part's not that hard. So the next step is, we're gonna walk through generating a spectral library from data. So I'm gonna exit out of presentation mode and show you how I do it on this computer. And I'm not going to be able to see everybody, so yell out if you need help. And Lindsay and Tina can also come over and help look at your screen if you're having problems. All right, so go to the files that you downloaded from the thumb drive. And I think we're doing, yep. Open up the plasma directory. Okay, so under plasma and then plasma spectral library, there are a bunch of files. We kind of try to set this up like a baking show, where we show you all the ingredients and we walk you through step by step, and without you actually having to do it all, we also have a final product. And so that's kind of what this represents. So the searched data, we want to make sure that that is accessible. You might have to extract it. Oops. Oops. Extract. Yes. Okay, cool. So you're going to have recordings of me going, oh, wait, what? Don't do that. Shit. Okay, so in the Skyline, we'll open up, and this is where, when you're doing just familiarization and you're not particularly targeting anything right now, this is a good place to start. So we'll go, okay, blank document. All right, everybody's at least up to here, right? Okay, so if you go to settings and peptide settings, and you go to library, you see the tab under peptide settings called library. You're going to build a library. You can call it anything you like, really. I'm going to just go with the date so we know, and a test. And then the output path, this just tells the software where it's going to go above its name. So I'm going to put it in the documents directory where all the other files are. And then cutoff score. So this is kind of like the quality score of the peptides from the spectral database searches that you did on the discovery data to generate these spectral library files. So the cutoff score will range from 1 all the way down to 0. Obviously, the higher, closer to 1, the better. If you don't want to have matches that don't look so good, then you can keep it at the default 0.95. If ever you have a question, it's always good just to start with the default settings in Skyline if you're not really sure. All right, and then we go next. We're going to add files. And under Plasma and the Plasma Spectral Library, you see the directory that says searched HRAM for Spectral Library. You're going to go in and just select them all. So these files are .msf files. They're results files generated from Proteome Discoverer, which is the thermo version of search engine that will evaluate the quality, identify the peptides, and so on. If you look on the screen over here, the data formats can be of a variety of types depending on what software you're using. You can extract pep.xml, pep.xml, .dat files. So as long as whatever search software you're using puts the peptides in this format, you're good to go. All right. And then we go open. And so now all of these searched files are in here. These data, oh yeah, go ahead. If you keep clicking through the folder, like it's zipped up in a folder, you can select the directory, or you can go in and select all the files depending on what option you chose. Hold on, I can't hear very well. Oh, that's the library. So you need to go on to, oh, you have to go on to the next in order to find all those files. So what you were doing is you were selecting a library that already exists and calling it that. So if you change the name, yeah. Okay, no, that should be fine. Just go to next.
Oh, that's fine.
Yep, oh, that's fine. Oh, so hit browse, and you have to make sure it's in that documents directory or wherever you're saving everything. Just go to documents, which is right below the desktop that you just clicked on the left. Yep. Oh, okay. But once you update that directory, then hit next, and then you should have access to all those files. You got it. How many people having problems finding these MSF files? You are?
I think I found them. I just think I have to extract everything, right? That seems to be the issue. Yeah.
Okay.
They're still zipped, which I didn't
Yeah. You might have to do that.
So I think it's giving that.
Okay. If you haven't extracted the files from the directory that they're in, you may have to do that. Okay. 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 Let's see. You want to go to library. You want to build. If you can type in a name for the library, it doesn't really matter what it is. Okay. And then we're going to make sure, where are all of the files that you downloaded from the site? On downloads? Documents.
From the website.
Okay. They're,
Not there.
okay, that's fine. And then downloads. So it doesn't look like there's any, oh, okay, hold on. So if you can find probably one of these, 10 maybe. I think you have to unzip those. So if you can open up that directory with Windows Explorer, just unzip it.
Okay, so unzip this.
Yep, unzip it. And then there'll be a break. I just want to get a little further and I'll come back and help, okay? Okay, don't freak out if you're not keeping up. I'm just going to move it a little further along so people have something to look at, and then we'll go around and help those that haven't gotten to this point yet. But once you're here, you've selected all of these input files. Because these are the only files in that HRAM searched data directory. We also could have just said add directory and clicked that folder, so that's another option. And then you want to make sure they're all selected and then click finish and then OK. So now you can see over here there's a status. It's parsing the spectra and it's building the spectral library. This data set represents a plasma digest that was fractionated by basic reverse phase offline into 48 fractions, and then each of those 48 fractions was run on either a Lumos or a Q-exactive. So we have high-res accurate mass data that has been fractionated. I think the plasma might have been depleted too, I can't remember. But the idea is we should get a good number of peptides and proteins. So it usually gets a little update when it's totally done. You can see the progress bar over here. Skyline has a lot of information to help maintain your sanity if you know where to look. Now, the other thing is we need to populate our targets, right? So we have a spectral library, and we'd be able to look through all the spectra that the spectral library has in it. But if we want to build a targeted method, then we have to add in some targets. So let's go see. There are a bunch of ways you can add in targets. One way is if you know what the target is and you have the peptide and protein sequence, the easiest way is to go insert peptides. And you could do FSNLK. So this is one. You click check for errors. No errors. Insert. So it put the peptide sequence in there. But it doesn't really have any way for us to monitor it because it's just the peptide sequence. So if you right click and go pick children, take these out, right? So the little funnel guy and this magic wand with the thing through it, I don't really know what that is officially called. Those might be clicked, so if you unclick it, so you can see all the precursor options, this shows the +1, 2, 3, 4, 5, and 6 charge states. Right, is everybody with me so far? All right. So usually we see the +2 and the +3 charge states. So I will select those two and then the green checkbox. And so now those are showing up. If you click on the plus sign, the expand option at the precursor mass to charge level, just for nomenclature, when I say peptide, it's going to mean click on the sequence. If I say precursor, it's going to mean click on the mass to charge of the precursor. And there will be times when those two things are different, like if there's 2 charge states for every peptide. So anyway, you can choose. Right now, Skyline has been set up to pick the product ions based on the information that are default given into it. So at some point, we might have said in here that pick the 3 best product ions that all have a mass to charge greater than the precursor. Now, does anyone know why we look for high mass to charge product ions? No analytical chemists in here? Come on. Right, so usually when you look at a full mass spectrum from low to high mass to charge, there is a lot of additional peaks, what we call chemical noise or electronic noise that's present in the low mass to charge range. So we don't normally pick those because of the potential for noise interference, and also they're usually less selective for the peptides. So usually you can use settings in Skyline, bless you. If you go into settings, peptide settings, you can do this filter option, right. And so this allows you to set, if you're working from proteins and you want to get to peptides, it sets a minimum and maximum peptide length. If you're working from a protein FASTA file, it'll say exclude the first 25 amino acids from the N-terminus. This is because many people that work from proteins in like cell lysates or plasma or whatever, there are a lot of exoproteases in samples that will just go nom, 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 nom on your protein from the ends in. And so oftentimes you won't have the N-terminus that was expressed originally with your protein. So we usually exclude that because it's highly variable. Exclude potential ragged ends means if you have a sequence that has like KR or KLK, whereas there's the potential that it'll cleave at every lysine, or it'll have a missed cleavage. It'll exclude peptides like that because usually that'll split your signal up into multiple signals for one basic peptide. And then you can also exclude amino acids, like Christina had pointed out, ones that can be modified, like methionine or cysteine. If you can look at any other peptide in your protein that doesn't have these, then go for it, because that will help minimize variability. The library modifications is also if you've carbamidomethyl. That's fine. If you alkylate your cysteines, you can use a carbamidomethyl or a carboxymethyl, depending on what you've used. Many of these modifications are already predefined in the drop-down menu. So does anyone use iodoacetic acid versus iodoacetamide? Yep, so the default in Skyline, I think, is iodoacetamide. So you'd want to go in and change that to iodoacetic acid, but most of these are all laid out as pre-configured options. If you have something that's specialized, you can put in an elemental composition for the chemical formula for something, and then that'll calculate the monoisotopic mass and the average mass, and you can assign it to an amino acid. So that's for things like if you're working with a company or with a researcher that has got a new reagent to specifically label proteins to make them so much more sensitive in the mass spec, and it's not commercially available, this is where you would add in those modifications. Yeah? I just typed. Oh, yeah, so it's, hold on. Cancel. So to add something simply and manually, you go to Edit, Insert, Peptides, and then you get a table. And the peptide sequence has to be the basic 21 amino, I don't forget how many there are, normal amino acids. It doesn't have to be triptych peptide here. You can just type in something that has amino acid sequence. You don't even need to necessarily have a protein name. Okay. So while we were doing that, our library is complete. It's finished loading.
Sorry, can we run through the picking children, unchecking and checking things?
Sure. Yep. So once you get that peptide sequence in there, if you right-click on it, you'll get this drop-down, and then you get Pick Children. So picking children of a precursor means you get to pick the charge states that it's possibly theoretically going to exist in. And so Skyline does all the math for you, but it can't really predict which charge state will be most intense. So we empirically gather that information and then figure it out usually, or we can compare it to a spectral library. All right? Everybody all right? Okay. So I picked the +2 and +3 charge states, and now Skyline, again, by default, is automatically giving us 3 product ions, but let's just say we want to pick more. So select the 477 precursor and right-click on it and pick children. And again, you'll have to undo this filter in the magic wand so you can see all the product ions. And now you can see, again, theoretically, what is possible to be generated as a product ion for this peptide. And first it's listed high to low mass to charge for +1, and then high to low mass to charge for +2, and these are all Y ions. And so I might add in a couple of those. It also, below the Y ions, will list the mass to charge of the B ions. So if you think you might observe some B ions, or if it matches the spectral library, you can check that. Okay. And so yours don't have to match mine. I'm just clicking stuff to show options here. All right. Now, because that spectral library hopefully is loaded for everybody, let's just go have a look at it. So if you go to the View option at the top of Skyline, and you go to Spectral Libraries, you're going to have this Add Modifications pop up. For right now, just hit Cancel. And so does everybody see something like this on their Skyline file right now? You're good? Okay, we have some success. I'm shooting for 50% success rate here. Okay? All right, so right now, because we don't really have many targets over here, these are all the peptides that were identified after running the high-res accurate mass and then the database searches. So you can see that the quality of some of these is not so great. Like this is a peptide that has only a few product ions labeled. One thing you need to note is when you're generating a spectral library from scratch, if you've never done it before, the default things that Skyline is going to label are shown by these box numbers over here. So right now it's only labeling singly charged Y ions, and that's not the only thing that's generated when we do MSMS. So click on the B. Now we've got more things labeled. And you can also click on the 2, which will give you doubly charged product ions. These are all valid. There are general rules of thumb about why people picked Y product ions or product ions that are not loss of water, loss of ammonia. I've never really stuck to those rules. I always look at what the data tell me. If it's reproducibly generated every time and I see it every time, then even though people might think it's not stable, well, I'm going to prove that it's stable and I'll use it. Or I'll prove that it's not stable and then buy them a beer because they were right. So you can see in this file, we've got a lot of peptides. This is page 1 of 70, and it's got the little elevator bar. So there are a lot of peptides in here, and we've got 6,940 peptides total. Yes?
Sometimes there's more than one PSM from a DDA search. Does Skyline go through and choose best ones, or do you average?
So as an example, so for things that are modified, you see this series of peptides here that has the QANK at the back?
Yeah.
All right, so what is underlined is where the modification is, and where it is underlined and the spectrum that correlates with it is usually matched from the database search with site localization confidence. And so if it was able to, I guess there's only, if there were like 2 amino acids that could have the modification and it was only found once in the peptide, it would only show you what it could confidently point at 1 amino acid. If it was detected at both, then it would show you 2. Yeah, that's my understanding.
Okay.
Okay. Okay. So let's see. Other ways to add targets into Skyline is to import a FASTA file. So if you go edit, insert, oh, hang on, don't do this because this might not be the right one. That's a copy paste. If you have a single protein FASTA file, you can copy paste the amino acids right into here in the FASTA file format, and that will get your targets put in here. The other way is by bringing in, importing a FASTA file. So if you go File, and then to Import, FASTA, and there should be a FASTA file under Plasma. So can everyone find from that flash drive in the Plasma folder, there's one that's called Uniprot Human Proteome FASTA. Okay. Everybody get it? And then you hit OK. And so what it's doing now is it's taking that FASTA file, it's digesting it according to the digestion parameters. I can show you if it'll let me. It won't let me. So it's digesting it in silico with trypsin. It's giving you peptides that are between 8 and 25 amino acids long. It's ignoring the 25 first amino acids of every protein present in the file. Oh gosh. Okay. And now it just imported all of the proteins that are present in that FASTA file, as long as they meet the same parameters for digestion in the software. So if you click on the first protein, it'll give you 1, 2, 3, 4, 5 peptides from that protein. And if you look at this little spot before the sequence, it looks like a little spectrum right next to the the YP thing. So that means there's a spectral library present in this stuff, in the data, in the spectral library loaded, in the data that were generated. And so that means we have empirical data to move from. So if you click on that WFY peptide, we can make this big. You can see what the actual spectral library looks like, what the spectrum looks like. And Skyline has gone through and ranked all of the product ions. So if you were to build a list, you would know where to start from. If you expand that first peptide a little further, so what Skyline is recommending is the Y7, Y5, and Y1. And looking at their intensity, it says Y1 is the most intense, so that should be on the list. But I disagree. Does anyone know why I disagree? It's not only too small, but for this peptide, it's arginine, right? And when you digest a whole sample with trypsin, like half of your peptides end in arginine and half end in lysine. So the selectivity of picking Y1 of arginine is very poor. So usually if you were to pick product ions, like the higher mass to charge you get, the more selective it is because only a certain number of amino acids can fit to make that mass to charge. So I can go in and I can pick children. So I'm going to get rid of that Y1 because that's just silly. I might add a Y4 and a Y6, and now I've got those in there. So there is manual adjusting you can do, but if you wanted to tackle it from a more high throughput way, based on the algorithms, you can go into settings and transition settings. So if you go to filter under the transition settings, this is where you can globally set the criteria for picking product ions or transitions. So if you wanted to look at your data dependent runs to see what chromatograms you could pull out that match these spectral libraries, you could, for the precursor charges, right now 2 is the default. I would put a comma 3. So now it's opening up all of my peptides to +2 and +3 charge states. The ion charges, usually they're singly charged, but if we look at 3+ precursors, we often see 2+ product ions. So I'll put a comma 2. And the ion types Y, if you wanted to look for Bs, you would put Bs in there. If you wanted to see the signal from the MS1 scan, so it's only looking at the precursors, you could do that too. And if Skyline is pretty, hold on, I don't know if it'll do it. If you hover, yeah, there we go. So you see the ion types, this box popped up, a list of comma separated product ion types, A, B, C, X, Y, Z, P for precursors to use for calculating potential product ions. If you wanted to just look at the MS1 scans, you could put P in, and then you would only see the signal from the precursor. I often do that when I'm loading the high-res accurate mass spectral libraries in so that I can go and see, is there really a peak for that particular peptide, or is it just kind of, it fell through the cracks and it looks like it's a good peptide, but in actuality it's not, because that happens too. Then for product ion selection, there's this from to. So from mass to charge greater than the precursor, that means all your product ions will be larger than your precursor. 2, 3 ions, and I never really understand what this means. So
When they very first started Skyline, it just kind of got like hard-coded.
yeah. So I go to from everything larger than the precursor to the last ion. And so that's pretty much like your whole peptide length. Some of the terminology takes a little getting used to, and I still haven't gotten used to it. All right, and then if you wanted to exclude where you're, sometimes we see on like ion traps, for example, if you're doing like Orbitrap, ion trap, MS2, you'll see loss of water from your precursor as a pretty decent peak. And you can exclude that mass to charge range, so you can put that in if you want. I usually just leave it blank because I don't really work on a lot of ion traps. And then library. So here we've got an ion match tolerance. We can make, yeah, so 0.5 is meant for the product ions, which are often generated in an ion trap, which is not accurate mass. So that stays a little bit higher. This checkbox, if a library spectrum is available, pick its most intense ions. It's kind of common sense. It just does what you're telling it to do. Pick 3 product ions. So I'm going to pick 8 because it's always easy to get rid of information that you have versus going back and having to redo everything. And the minimum number of product ions. Some peptides are short and you're not going to get more than 4. So I at least put 4. And then this section is a bunch of choices. You want to pick the ions from filtered ion charges and types, from filtered ion charges and types, plus filtered product ions from filtered product ions. So it pretty much looks at precursor criteria and product ion criteria. So if you select that middle one, there's a good chance you get what you need. In this instrument, min, max for mass to charge, this is related to how the instrument, so if you're running a triple quad and you want to take discovery data, maybe the discovery data was generated by scanning up to mass to charge 2000, but your triple quad has a high M over Z range of 1800. Then you want to tell it, I don't want to see any ions over 1800. And so you would go in here and you would put 1800. The default is 1500 because that's what some of the instruments are at. So just make sure you're aware. If you're seeing good product ions and your triple quad or whatever can detect it, update this number. And then the method match tolerance. This is for precursor, making sure that everything matches with high mass accuracy. Firmware transition limit. This is related to if you know that your instrument is incapable of doing more than 200 transitions in a method, then you put that number in. This was put in there a long time ago when there was a hard limit of 200 or 1,000. Now it's up to like 10,000 or 30,000, so you really can probably leave this blank. It's not a big deal. And the inclusion, I'm not sure what inclusion limit is. Most of these have explanations if you hover over them. And then, yes?
Sometimes increase the minimum M over Z from 15? Or do you leave it?
I leave it because I'm not entirely sure what that controls, if it's reading in data or if it's putting it out into a method. So if you're reading in ion trap data, I want to make sure it goes all the way down that low just so I get as many matches as I can. Of course, you could adjust it up, but I'm not sure what the impact on that would be. Bless you for the target instrument. Yeah, so you could truncate it to like 300 if you're not scanning below 300 for a triple quad.
Why 3 ions, for example, if it's very intense, but you don't want to have it, but I don't know what it does while reading data.
Yeah, I think what you're suggesting is correct. If you set it higher than 50, then it will not select ions that are lower than 50. So, all right, and then so the full scan option, this is something that was incorporated later, as Tina had said. Skyline was originally made for selected reaction monitoring, and so full scan wasn't really an option. But now with the advent of PRM and all of this jazz, it's here and it works really well. What I like to do if I'm generating a method on a triple quad, but I'm starting with discovery shotgun data, I make 2 Skyline files. And in the file name, I will put full scan or Orbitrap or whatever the mass analyzer was that generated the data. And then for the triple quad one, I will either do SRM in the file name or triple quad QQQ so that I know that this full scan option is enabled for my full scan data set. So what does all that mean? Skyline is, if you have these targets and you don't have this full scan option enabled, it's going to only filter for the product ions. It's not ever going to look for the precursors unless the precursor is listed as a product ion, if you've listed it as that. So that's one thing to note. 2 is, was that the only thing? If you are using this full scan option and you're analyzing a data dependent file, you don't really need product ions, right? Because you're only going to get 1 or 2 scans for every peptide in MSMS mode, but you're going to get a lot for the precursor. So it's a little challenging to go back and forth and change these settings when the data are already imported, because if you change these settings, you have to re-import the data. So this is why I'll have the same target list, but 2 distinct Skyline files to compare and contrast. And then here, yeah, so let's just walk through this for a second. So isotope peaks included, I usually set this to count. So this will look at the monoisotopic peak, the M+1, the M+2, however far out you want to go. I use count because it's what I like to do, because I know I'll be able to set a certain number. The other option is percent. I usually pick 3 if I have a large number of targets. Sometimes I'll pick 4 if I have a smaller number of targets, just so I can make sure everything looks good. This is in part what Skyline uses to generate that dot product on a precursor. It's looking at the M+H, the M+1 and the M+2 and their ratios to one another to generate a dot product. And mass accuracy, here. Depending on what mass analyzer you're using, you need to specify. Orbitrap has this weird, you state the resolving power at whatever mass to charge. This doesn't have to be the resolving power you acquired at. It can actually be tighter. Okay. And then MSMS filtering is pretty much the same. You tell it whether you've done targeted or DIA so that it knows how to process the data. And so if we do targeted, you again specify the mass analyzer. Or if you've done DIA, same thing, but you fill out the isolation scheme.
So for the number of peaks in the MS1 filtering, like the smaller the number, the more inclusive?
Yes. Sure, the question was, for this number, the number of peaks for the isotopes that you're looking at from the precursor, if it's a smaller number, like you say 1 or 2, then it's going to get more data. So that's a double-edged sword, because the way you look at full scan data with Skyline is you'll have better confidence in identifying the proper peptide the more co-eluding isotope peaks there are, right? So if you just say, show me 1, you're going to have 1 color extracted ion chromatogram with tons of peaks, and Skyline's only going to pick the tallest. And as we know, the tallest is not always right.
And then for the MSMS filtering, if you're only interested in the MS1, like if you're using DDA data, then this part doesn't matter. Like you would put none for here.
Right. If you're just looking at the, so the question was, if you're just looking at DDA data and you're only interested in the MS1 profile, you would leave this as none, the MS2. Okay. So what I'm going to do is so that just kind of goes over some basics of setting up targets. The other ways you can input targets into the list is by going edit, insert, transition list. If someone has a method and they've already got the list worked out, you can just paste it in here very simply from an Excel file. Yes? Oh, yeah, sorry. Say okay now. Yeah, or cancel. It doesn't really matter. Because this is just familiarization and playing right now. Okay. Any questions about this so far?
Another question.
Where is it? No question? Okay. Oh, all right. Okay, so we've generated a spectral library from the high-res accurate mass search data. And so here we've got all targets that were in that spectral library file And then we have put in the FASTA file. So anything that's in the Spectral library that's in the human proteome database is matched and put in there. So it's a lot of stuff. It's more than what we need. And so then we can kind of focus on, well, if we're going to be targeting things, we want it to be more of a hypothesis-driven setup, like how much is something changing peptide X, and then monitoring that. And so for this process, we go through this refine, optimize, and refine. So this was an example I had up there earlier, which was in the Spectral library, we might have a +2 and a +3 version of the same exact peptide. And this is a trade-off. This one has a lot more product ions that can be monitored, especially of higher mass to charge. This one, you can see why here there's a little bit more noise, peaks that are not labeled down at the low mass to charge, which is why we don't like to pick these because of potential interference. But these are much more intense, like orders of magnitude. So how do you know which one to pick? And this is one of those things where you don't always know. And so if you have the luxury of picking both and seeing what the data come out on your instrument, and then getting rid of the one that seems less sensitive or less reproducible, then try that approach. Yeah, with that said. Oh, so this is the one reference to the dot product and how it's calculated. And there are different ways to calculate dot product, and Skyline uses dot product in a couple of places. So here's an example like Tina was showing. We've got a peptide, and Skyline has picked something down here. Skyline always picks with a little black flag. If we zoom into the potential other peaks, you can see what the dot product, 0.16, 0.92, 0.37. And so usually the dot product is the first indicator for picking the correct peak. The other thing I use is, even if a peptide hasn't been observed in a Spectral library, there's this awesome correlation with the hydrophobicity that is calculated in Skyline for your peptides versus where the actual peptide comes out. And you see the regression is pretty decent. We get like 0.9 correlation coefficient. And this is interactive. So if you have data where the peptide's been selected in a chromatogram and its hydrophobicity has been calculated, which it is by default, you can click on any one of these peaks and it brings you to that peptide and it shows you the chromatogram. So if you have outliers, which are usually shown in purple, you can click on them and go to that peptide and say, oh, are there any other options? Maybe Skyline picked the tallest, which it usually does. It also looks at overlapping dot product and mass accuracy where it's applicable, but it still doesn't always get it right. So to save time, what I do is I'll look at this, and I won't go through peptide by peptide initially. I'll go through all of my outliers, and I'll be like, correct them if it looks like they can be corrected. Yeah, so if you start measuring peptides with a targeted list and you see a couple of cases where you have overlapping transitions and like, oh, that could be a peak or it could be this one over here, which one would it be? So going back from the previous example, we had this one at 45, 50, and 35, all pretty different retention times. If we look at options, so this peak at 42 minutes had a dot product of 0.92, and that's where it falls on the line. If we picked the one at 50.9 minutes, the dot product is crap. And if we pick the one at 35 minutes, again, the dot product's lower, and also it's far off the line. So it's just another way you can use your data in your targeted method to make sure that Skyline's picking the right peak.
How well does that work for multi-peak peptides?
Not well at all. And that's where you would want to include the index retention time, which we'll get into, or the IRT option, but that will help a lot more. Yes? Oh, how well does this work for modified peptides? And the answer was it doesn't. So if you have phosphorylation, glycosylation, it ignores that. So you can have, like, I know phosphopeptides will have different retention times depending on which site is modified. And some of them may coelute and some of them may chromatographically resolve, and this cannot predict that. There may be other calculators that can, but usually measuring the empirical retention time, and then using IRT will like nail it every time. Yes?
It shows auto navigate Skyline to get to this particular, how to get to the SSR.
Yeah. We will get there.
If you have an indexed retention time, will the peak picking of Skyline be influenced by that?
Usually, if you use indexed retention time to help predict the retention time in the method and you schedule it, Skyline has fewer options. So you're not generating. Yeah.
Skyline picks peaks by storing stuff up. We'll talk about this tomorrow. But it just is taking a tally of whichever peak and highest score is the winner that picks. And retention time is one of those scores. Guys,
Okay.
I like scooping all the stuff we're supposed to
I know, like settle down, everybody. Gosh. So these are just some more examples of which. So I think I deleted out which one Skyline would pick from here, but you know which is the proper peak, and we've been through a few examples, so I'm not going to spend a ton of time on it. What I do when I see something like this is I will take my eye and I will look at the baseline signal, and anywhere there is a complete liftoff of all the signal for the product ions, I'm going to be like, oh, that looks reasonable, because it's not often, if you choose product ions from a spectral library, it's not often that they are completely unobservable. So, you know, one like this where it's 2 or 3 product ions have absolutely no signal, it's unlikely, in my opinion, that that's the right thing. But it's also trial and error. Some peptides just don't behave. So in this case, the peptide at 33.7 over here, this guy, has very low signal, but we can see from the information it's got a dot product of 0.73 and it falls right here. Not on the line, but a lot closer than any of the other peptides would be. Here, all right, so 0.41, 0.88, 0.68. What do you think? Come on, it's practically spelled out for you. Look at the dot product. Oh my gosh. Right, so this is a case where if you're not really sure, well, let's look at the retention time information. This big peak falls practically on the line, but it has a low dot product. And this little peak, whose signal completely lifts off from the baseline, is further from the line, but has a higher dot product. So like, which one is it? Yeah, I don't know. I would have to go and like find out, potentially have standards, do like different spike amounts of this into maybe a different matrix to figure out which one is the right peak. So it's not always straightforward, and you're not always going to nail it every time. And this is why it is called research, right?
In order to check those several different possibilities, you're just manually moving the integration window around. Is there an easy way to do that?
Hire someone to do it for you.
If you can't, or you're the person that's hired?
Yeah, so I've always been the person that looks at the data, and this is where I try to use these kind of plots where I'll only focus on outliers first of all, so it minimizes the need to do all this kind of work.
But as far as like moving that flag from one peak,
Oh,
you're just
it's reasonably straightforward in Skyline. We can show you shortcuts of zooming in and zooming out, and then if you hover over here, it turns into a hand, so you don't have to integrate. Skyline will see a peak, especially if it's labeled, and you just click that, and it integrates it. But it's hard with large data sets and low signal to noise stuff. It is challenging. But if it was easy, everybody would be doing it, right? All right, so now we don't have spectral libraries, so we don't have a dot product. What peak is this one? This is like back to Tina's example, and like we don't have anything for this. What would we want to look at? Maybe look at the retention time relationship. So the one at 37 minutes is out here, and 43 minutes is even further, 45 minutes is even further. And so this one, I have a green check next to, and to be honest, I'm not really sure why. Does anyone have any ideas? Look at the data. Right, this one is not lined up with the purple one. So the purple one is maybe an interference and maybe causing some problems. This one, the apex of this whole cluster is not lined up, so it's unlikely it's this, but Skyline might pick it because it has a whole bunch co-eluding right here. And so this might be the best option. And I probably figured out a way to verify it, but clearly not easy. All right. So we should have, let's go, Lindsay and Tina. I know like we started late. How long should we keep going for this? Flag me when you want me to stop. Okay. Then we're going to be here until 8 o'clock tonight, everybody. Let's see. Searched, data, plasma. Okay, so there's a file called plasma CE optimization. It's a zip file. You might have to extract it. And there's a .sky extension and a .skyd extension and a .sky.view extension. Just nomenclature-wise, this .sky is the document. It will open up the big window with the targets on the left and the data on the right if you have the .skyd with it. This contains the data, and then the .sky.view is the layout that is automatically saved when you close your Skyline file. All three of these need to be in the same directory, so if you begin moving things around, stuff will get disconnected and corrupted. If you're transferring Skyline files, there is a file share option that'll zip it like this and keep it all together, just so that you are aware. If you want to open it from a file directory like this instead of Skyline, you would double click on the .sky file, and it should open it up. Oh no. If you get this document requires the QE plasma, blah, 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 just hit cancel. Oh no. Maybe not cancel. Let's try that again. Open, just hit open. Oh my gosh, okay. Oh my gosh. We should make everybody report that error because it'll go ping Brendan right now. All right. Yeah, so for some reason this is disconnected. That's all right. Yeah, it could be because it's zipped, you're right. Let's see. All right, let's try that again.
Yeah,
So,
it's not it's working on it.
oh, thank goodness, okay.
I just extracted to the same folder.
Yep, okay. So if you haven't extracted, extract it. This shouldn't take too long.
While this is happening, sorry, I have a possibly silly question. How do you, in the first example that we were doing where we wrote in the peptide, how do you populate the window showing the chromatograms?
Oh, okay, so the question was,
Right now I just have my MZ traces.
you have what?
Right now I just have my MRC traces.
Yes. So the question was, how do you get a chromatogram in for the target peptides once the peptides are in that target list side? And it's file import results. And it would have to be a file that had targeted,
Oh, okay.
had that data in it. Otherwise, you get nothing.
So we can't use it with this example. We just
Right, not yet. We will have other examples that we can show you how to do that with. All right. All right. You also, it is possible to have more than one Skyline file open at any given time, just so that you know. Okay. 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 What am I doing? Transitions. Okay, this is an example that is looking at a bunch of peptides that were targeted, and we optimized the collision energy of the product ions. And so usually when I set up a targeted method, like I had mentioned, I start with 8 product ions, particularly if I don't have standards, because the more product ions you have that match, the more confidence you have that the peptide is the one you're trying to detect. once I'm confident in that peptide, then I will reduce the number of transitions so that I can like quantify on the most intense 3 or 4 or so on. In this example, so this is peptides in plasma. It's an ass peptide. I don't know why. This one, the peptide name starts with ass. So I just think that's really funny. I probably had that highlighted on purpose when I was like junior high or something. Anyway, so if we go to the top and you pick that LIY peptide, so some shortcuts that are super handy for Skyline is if you want to zoom in and see what that little peak in the middle looks like, hit F11. Oh yeah. And then if you want to zoom out, hit Shift F11. So this is really quick toggling back and forth so you can zoom in. So when I zoom in with F11 and I'm like, hey, I don't think that peptide looks very good. If you have a little roller ball on your mouse and you put the crosshairs in the chromatogram, you hit Control and then roll down, you can kind of quickly move things back and forth. If you click and hold and move it left and right, it changes the x-axis. Right now, this is auto-scaled to the most intense peak in the chromatogram. But this, for me, just helps, like, if I want to look around and find any other peptide. So the question over here was, if you have to do this manually, how, like, this helps take some of the pain away. Not a lot, but it helps make it a little bit easier. So Skyline picked this peak. It shows its dot product compared to the library. These different colors are all the contribution of each of those transitions to the total signal. So they're compared side by side with the same total intensity, and it shows you how the signal's breaking down. So if you see big changes, like this purple one is more intense in the spectral library than over here, it's something to consider. It might be an interference or something funny might be going on. So the way that we generate, we optimize collision energy is by using Skyline, which is super nice. And if you go into, let me just make sure before I tell you, filter prediction. Yeah, so under settings and then transition settings, there's this prediction tab. And there's a collision energy option. So collision energy has a good relationship with the mass to charge of your precursor and the charge state of your precursor. The bigger the mass to charge, the more collision energy you need to appropriately fragment it. This is critical on a triple quad because you can optimize per transition, not per precursor. And unlike ion traps or orbi traps or TOFs, you fragment once and gather all of the ions. With the triple quad, you're fragmenting the precursor and detecting one ion per fragmentation at a time. So you can use different collision energies for different product ions. The downside to that is once you start optimizing and getting different intensities, optimized intensities for your transitions, your dot product may go down. It won't match your spectral library as well because now you're like trying to intensify all of your product ions and they won't have the same pattern as they do in your spectral library. But that's not a big deal because by the time you get here, you should be confident what you got. So for collision energy, we pick the instrument that you're using. The reason these are here is somebody has already done the experiments to figure out what the regressions are for these instruments. So to know precisely what they are, if you go to Edit Current, this little guy pops up and it'll show what the slope and the intercept of your collision energy regression equation is for the +2 peptides and the +3 peptides. What this will do is this will generate a collision energy based on your mass to charge for the +2s and a slightly different for your +3s. All right, and then that's what it'll be set at to generate your product ions. But it'll be one collision energy for all of your product ions. There is a way to optimize it on a per transition level, and we start here in this window. So under optimization, we have a step size, which is in volts, so collision energy volts. And then the step count is you use the equation to set your like default collision energy, and then this would be an example of going up 5 steps in 1 volt increments and down 5 steps in 1 volt increments to generate a total of 11 different collision energy values. Then it would acquire the data, plot it, and show you what collision energy provides the most intense product ion. So it's kind of all automated for you. Usually, in my experience, 1 volt steps are like a little too small. I would go 2 volt steps, and I might do 4 on either side so that you can get over a broader range and you can really make sure you measure the apex of the breakdown curve. So let me show you some information. Where's the collision energy? We'll get to this. So if you were to infuse a peptide and monitor its product ion intensity versus collision energy, which is how we used to do it in the old days, you would plot these data and get this like Gaussian distribution where it's not super broad up at the top, but this helps you define the apex collision energy for generating a particular product ion. And the collision energy may be different for each product ion. If you take all of those information and plot them, then this is that regression I was talking about, where you get a slope and a y-intercept, and you plug in your mass to charge, and y is the collision energy value that you would use. You can kind of see the mass to charges of different peptides, maybe with different modifications or whatever. They might not all completely fall in the line, but it's usually a good enough fit to give you a good starting point. Optimizing can help you get further. So this is what we were just going through in Skyline, showing the different options and the different step sizes you can look at. So if we go back to Skyline, I'm gonna, show graph, yeah. So if you click on the show graph option in Skyline, these data are how those regressions were generated. And you can redo this. You don't have to rely on these. So if you're not sure of where these data came from or who did it, if you were to optimize your own empirical data and you had the information in here, if you clicked use results, it would change the plots based on your data that you put in and show you new graphs. Okay, so I'm going to cancel out of this and cancel out of this. So let's go find a peptide that okay, there's a good one, right? We like this one. This looks nice. I'm going to just get rid of that. So these data were generated with multiple steps of different collision energy values. But you can't see that information right now. We have to change the way Skyline is looking at it. So if you right-click anywhere where the chromatogram is, and you go down to transitions, and you show, right now it's showing all. So it's showing the signal for every one of the product ions or transitions that we monitored for. If you change it to single, you see now that everything becomes much more colorful. Yes? F11. Oh, or I don't know if there's a way to like, auto zoom x-axis to best peak. Okay. Thank you, whoever said auto zoom in the back. Okay. So what this is showing is right now I'm clicked on this peptide at the peptide level. So it's showing me the signal from every product ion at the different collision energy values. And so you'll note the color red is always the default coming from the collision energy regression equation that's in Skyline. And then the different colors are step 1, 2, 3, 4, 5. So, right, you'll see the different colors denoting data generated at different collision energies. And again, this is at the peptide level, so it's assuming you're going to apply 1 collision energy for all of your product ions. If this legend up in the upper right is really large, so if you want to see this look a little nicer, you can click and drag it out. These are all movable windows. So you can see that semi-Gaussian distribution, like I had shown in the presentation, where this is the default, and we're getting better peak intensity at the peptide level, moving a couple volts down, lower in energy. So that might be something that we wanted to do. However, let me move this back over here, if I can. if we want to look at the different product ions, which is where the triple quad can win, if we click on each product ion, then what you'll see is, if we go back here, and you can kind of look through, most of them should have this same general relationship where maybe that brown one, whoops, is the most intense. This Y3 product ion, maybe it's not generating enough intensity to get good ion statistics to do this kind of calculation. Oh, but look at this one. The B4 has even lesser energy, generates better intensity for the B4 ion. So this is where you can really fine tune and get the most out of your triple quad performance. With PRM, or using full scan MS2, you don't really have this option unless you do multiple scans at different collision energies, and that leads to some more data analysis challenges. Are there any questions on this? Yes. I'm sorry? This is peak area. Yeah, peak area. And so it's looking at the transitions at the different collision energy, that transition I have selected. So have you right-clicked to transitions, where is it, and made it single? This is a critical thing you have to remember, and it's easy to forget. The default is transitions all. And so you won't see the data broken down this way. If you have it set to all, it'll look just like a regular chromatogram. So you have to make sure it's on single if you want to look at collision energy optimization. Okay. It depends on what your goals are. So for some people, a twofold improvement in signal is exactly what they need, and if they can gain it for doing a little bit of collision energy optimization, then it may be worth it to have access to those peptides at a low detection limit. For some people, they may be looking at high abundance peptides in a sample, in which case starting with the regression equations is often good enough. I have an example in here where it's like, what does it buy you? So this was a question I had early on, which was like, do we really need to do it? Because it's kind of a pain, and there's all this extra data analysis, and you need extra samples. Got to make sure everything's stable. So sometimes you get, like, this is before collision energy optimization, starting with the regression equation, and this is picking the most optimized collision energy per transition, and you get this, like, not even 10% gain, right? And then we looked at a bunch of peptides. And so this is for all of them before and after. And except for one case, it was all like very minimal increase. So if you do a handful of optimizations and you find like, it's not really helping, then you could just not do it. There are cases, though, that are these precursors that are triply charged and their product ions are doubly charged. And because the regressions are based on the mass to charge of the precursor and the charge of the precursor, the collision energy is overestimated. So for doubly charged product ions, we often see this skewing where the best collision energy is many, many volts lower than what is predicted. And like I've talked to Brendan about, can those regression equations now be segmented based on charge of the precursor and charge of the product ion? But there needs to be enough data to generate a regression to support that. And it's like, no one's gotten around to doing it, but if anyone wants to come up with a cool paper and give it to Brendan, then the numbers would be right in there and it would be awesome, just saying. And it's not just on one type of instrument either, it's on multiple instruments. So we came across this in the CPTAC study. Okay, so again, you can look at a single collision energy based on the precursor signal, and you get what you get, which is often good enough. Or if you want to tweak it and optimize based on the product ion level, and in which case your collision energies may be a little bit different. Right, and then post-translational modifications. This is case often where, particularly on triples, if you have a phospho group on your peptide, it'll ping off before the peptide backbone fragments. And so in cases like that, it just means you have to look much more carefully at your data and perhaps include some kind of standards. While they may not be isotopic versions of your peptides, you might have something that you can like use as a less expensive standard to just make sure what the instrument's doing to the peptide, and then make sure that your peptide is behaving similarly. So again, PTMs are a little more tricky. I haven't done much work on them because they're tricky. I kind of give up and change jobs when someone tells me to do that. So I'm just kidding. So in the end, transition selection and optimization are very important. We want to balance the sensitivity gain, like you were kind of alluding to, the sensitivity gains with the amount of time and effort you need to establish that it's worth doing that. So it's often important to step back and be like, do I really need a 10% gain? Or if I invest the time and get a 50% gain, do I want to do that? So a lot of kind of decision points to make. Worry about interferences. So this was one thing I kind of hopped over in this presentation. Early on, we asked Brendan if there was a way to look to see if there were interferences in our signal, because we're measuring parts of our peptide, and there are lots of other parts of other peptides that can interfere with the signal. So one of the things that you can do in Skyline is if you look at the peak area view and you right-click and you normalize to total, it'll take the signal from all of the transitions you're monitoring and make them all 100%, and then you can see what smaller percentage of each transition makes up the total signal. So if something doesn't have any interference, you would expect to see very reproducible across a whole series of samples. In the case of this peptide, this was the heavy version, and the light version should match exactly, pretty much. And so you can see over here, these 3 or so peptides samples matched really well with the heavy. What you don't know that I'm going to tell you is this is a calibration curve going from the blank with no light spiked in to increasing light as we go up and up and up and up. When we get to this point, that's when these ratios match with the heavy. But over here, there's this whole humongous interference from the purple transition. And so previously, we had been just looking at the peak area ratio in tables, so numbers in tables. And I black out after a while when I try to do that. So this was a nice way to visualize, like this doesn't match this. So clearly something's going on here. And when we went in and clicked on one of these and looked, we saw this humongous purple peak that was always there in the sample, pretty much at the same level until we got to a high enough peptide level that we spiked above that. So that's something to worry about. And then there are ways to look at the data when you're doing this refining process and looking at responses to see if there's anything funny going on in the data. In these 2 cases, when you see one transition, so each of these colors represents one transition for a total of 3 over a concentration range. When you see one transition lift away from the line like that, it's usually an interference. And so if there's just one and the rest fall on the line, that's usually an indication of one transition interference. If all 3 of them start stripping away from the line and it's a non-zero signal, like there's actually a peak there, that's usually indicating there's endogenous peptide in your sample, and that will not serve as a good blank. So you might want to look at some kind of alternate blank. Likewise, at the top end, if you have 2 of 1 or 2 or even all 3 of your transitions sort of tailing off, this is usually detector saturation. The red is the most intense transition. These are color-coded, followed by blue, followed by green. Because these are the most intense, they've saturated the detector and it doesn't go up linearly anymore. And so again, you wouldn't want to start measuring peptides above that concentration, right? No correlation means this peptide wasn't detected. We're really just plotting noise here. And here, this is what unstable electrospray looks like. If you have dropout in your signal, your peaks are too narrow, you may see a general relationship, but this is not something you would want to quantify with. Any questions? Yes?
Is there a situation where it's worth optimizing cluster potential? Like, you can also do that, but I don't know where you can do that.
if it's worse after optimizing. Is that what you're saying?
Yeah, like for triple charge, it's more likely that you gain something with optimizing collision energy. The clustering potential, is it also going to be some situation where it might be worse doing though?
Yeah, so another potential for optimizing collision energy is, this is rare, but if you have something co-eluting with your peptide, that's the same mass to charge but maybe a different charge state, it will co-isolate, and no matter what mass analyzer you use, it'll co-fragment. However, it may have a different optimal collision energy. And so if you can optimize for what you want to fragment and minimize what you don't, that is one way of using collision energy to like reduce interferences, not eliminate them. But the different charge states should have different collision energies, and so that's potential. Other than that, I can't think of anything right now. Yes?
Collision energy data that we downloaded, how was it generated? How do we do that?
Oh, right, okay. So Skyline will generate the list for you automatically. In settings and transition settings, we went through this collision energy dropdown, and if you wanted to edit this, like maybe I'll do 2 volt step size and step count 4. So this sets up the basis for what volts it's going to optimize on. You hit OK, and then go to File, Export, whoops, Transition List, and I'll run on a thermo. How many? I've got 493 transitions. That's a lot. So what I'm going to do is break this down into multiple methods and ignore the proteins. What this means is it won't keep, if I have multiple peptides for a protein, it won't necessarily keep them together, but I don't really care. And then maximum transitions per sample. This is dependent upon your instrument. If you're not going to schedule and you want to have, and you know your chromatographic peak width, let's say your peaks are 15 seconds wide, I like to see 1 point per second. And so depending on how fast your instrument can scan, I usually set it up to do one scan, one whole cycle a second. So for 15-second wide peaks, I'll have 15 points, which I'm very comfortable with, especially in the early phases. So let's see. That would, let's just assume I can, well, let's do 750. Let's assume I've got 1 millisecond dwell, 1 millisecond interscan delay, so that's 750 transitions per second. And then down here, there's this optimizing collision energy. And so you'll notice when I'm not optimizing anything, I have one method because my total number of transitions is 493. And when I say, no, give me methods that optimize collision energy, I'm now up to 7 methods. All right, and so these are unscheduled. It's easier if you have their retention times and you can do it scheduled, then it greatly reduces the number of methods you would run. And okay, so then I hit OK, and it'll say, all right, what do you want me to do? CE opt. I just come up with a name. It's going to save it as a CSV file. And then if I go back into that, where is it? So see, it made CE opt list. It automatically numbers them 1 through 7. And so then I would just put that transition list in my LCMS method, keeping everything else the same except this transition list. And if, I don't know if we can open with. This will give you an idea of how it does what it does. So precursor, product ion. You'll note that these are all 1088. So these 9 product ions are all the same technically, but Skyline is varying the 100th place. And that is how it knows the collision energy is going to be a little bit different. So each one of these pairs, this changes in the 100th place, and this changes by 2 volts. All right, so this is one product ion here measured over 9 different collision energies, and it goes through that the same way automatically, and so you don't have to worry about it. You just take these lists, import them, and then when you want to analyze the data in Skyline, you go File, import results. And then that first option is optimizing. Are you optimizing anything? You click collision energy, and now it knows how to parse the data out and plot it properly. And so you may have 7 runs now based on this experiment with 7 different methods, so I have 7 individual runs. I will import them all as one new replicate, and I will call them CE opt 02. It's kind of, yeah. And then when I hit OK, it'll say, show me those raw files, and you click them all, pop them in, and then you get that outcome. I think there may be raw files in that zip directory too if you wanted to import them. Okay. Where are we at? Yeah. What do we want to do? I don't know, I'm tired. All right. Oh, there are other cool things about Skyline you all should know. So, and this came from like us begging Brendan to do certain things. Thank goodness he's very accommodating. But if you right click in any of the plots, whether it's the chromatogram or the charts, you see this whole copy section. So there's copy, which copies that image in that aspect into PowerPoint or Excel. And it's high res enough that you can use it for publication kind of stuff and posters. If you click copy data, and then you go and paste into Excel, it pastes the actual numbers. So if you don't like the color or the order things are sorted in, you can't really change that in Skyline, but you can plot it yourself somewhere else. And that's super handy. I'm not sure what copy meta file is. I have not used it because I haven't had a need to. And then the save image as, if you need it, I guess higher res, or if you need it as a picture, then you can use that option. Yeah. That, oh, you mean in the, oh, it would have those tags on it. Yeah, yeah. Thank you. I learned something. Yes.
So if you go to your CEO one as you go through your transition, why? It's funny because in mine, when I change, it changes the whole intensity value.
Yeah, hold on. It's because I don't have it on single. Okay. This one?
Yeah, why does it change the
Because it's looking at those individual transitions. So that's,
transition will have different fragments?
no, so this is the Y6, and this is at, these are all at different collision energy voltages. And so this is either a super low or super high collision energy, and it's not fragmenting the way it's over fragmenting. The red is the default based on the collision energy regression equation. And then as you go up a couple volts or down a couple volts, you'll see the intensity change because it's either too much or too little energy. Yes?
So the collision energy optimization that we did not, this is fully based on what Skyline thinks it should be, and it's not like the raw file does not have any, like in the experiment, they did not try out all the collision analysis. This is something that Skyline is predicting that this might work.
Yeah, so Skyline is giving a range of these different collision energies based on that starting regression equation. And so for this first product ion, it's going in 2-volt increments. It's trying a different collision energy for that product ion. And then when it goes to the second product ion, the 1017 from that same precursor, it's going over that same range. And so these 2 product ions may prefer different collision energies for optimal fragmentation. And Skyline will pull that information out. So you can see we've got a Y11, Y10. If we go down the list, this is how the whole process occurs. And then when the data are read in, Skyline will automatically tell you which collision energy provides the most intense peak per transition.
So the regression line is intensity 5 and X is the collision energy.
it should be collision energy Y, mass to charge X. Yeah, so this is the +2 and the +3 collision energy, and then mass to charge that way. Does that answer your question? Yeah. Okay. The question in the back? Usually. So it's been evolving over the years where originally there was nothing. And so if you wanted a collision energy regression, it was on you to come up with the data to support that. And then a bunch of people with different vendor platforms reached out to Brendan and said, hey, I've optimized. Like I worked at Thermo, I optimized on the Quantiva. I gave him all the data, and then it became a function in there that everybody could access. Or if you have modified peptides that don't follow this and you want to create your own, you can create your own. But a lot of the ones that are in here are either generated from the vendors or independent investigators gave Brendan data and he put them in there. Yeah, so if you look, and there will be differences in different models from the same vendor based on their collision cell, what gas is used, the pressure of the collision gas. I know, for example, the Quantiva, the Vantage, and the Ultra, you could specify your collision gas pressure, and that will definitely affect the collision energy that you see in practice. And so you would want to make sure you're doing it the same way as what this was, like the default value.